In this video, we're going to discuss the fundamental theorem of calculus, which is a theorem that is fundamental to the study of calculus. And essentially, it is leading us back into talking about integrals algebraically again. Like we talked about earlier, the very first unit, the very first couple lessons, I should say, of this unit, we were looking at algebraic integrals. And we were taking antiderivatives and just looking at the functions that came from them and essentially what the opposites of derivatives were, etc., etc. And then we kind of went away from that. We went into this whole geometrical approach to it, looking at the definite integral and Riemann sums and looking at it as an area under a curve. And the fundamental theorem of calculus is what ties both of those two things back together again. So it essentially allows us to find integrals algebraically because we're not always able to have functions that are triangles or rectangles, or circles. And so because of that, if we're working with functions that are not those generic geometric shapes, the fundamental theorem of calculus comes in and says we can still find integrals the way we would normally do it algebraically. And then when we want to find the area under the curve, we would use this rule or this theorem in order to connect those two pieces together. So the integral still means the area under the curve. We might not have as much of a visual representation of it anymore in the sense that we're just looking at it algebraically, and then this is a very fundamental theorem that ties the two things together. So here's an example of a geometric one that we would be able to do. It says on your calculator, graph the function y equals 2x. Don't worry about doing it on your calculator for right now. We'll just kind of talk about it and look through it together. It says you would get the graph below. Now let f of x equal the accumulation function from 0 to x of 2t dt. That's this function right here. And it says complete the chart. So if I plug in 0, the integral from 0 to 0 is 0. That's this. The integral from 0 to 1, it has a base of 1 and a height of 2. And it's a triangle. So 1 times 2 is 2, divided by 2 is 1. The integral from 0 to 2, base of 2, height of 1, 2, 3, 4. So 2 times 4 is 8. Half of that would be 4. At 3, base of 3, height of 1, 2, 3, 4, 5, 6. 3 times 6 is 18. Half of that is 9. At 4, base of 4, height of 1, 2, 3, 4, 5, 6, 7, 8. 4 times 8 is 32. Half of that is 16. I'm pretty sure you get the point. This next one is going to, I guess there's a pattern down here, I should say. This next one is going to give us 25, and then the last one will give us 36. I won't prove it to you right now, though. It says, what is the relationship that you see between x and f of x? So hopefully you notice that when you square x, you get f of x. Square it. Square x to get f of x. There we go. It says, so it appears that the integral from 0 to x of 2t dt is equal to x squared. And again, I hope that makes sense to you. The derivative of x squared is 2x, or 2t. The integral of 2t would be 2t squared over 2, which simplifies to t squared, or x squared. So that's the relationship between these two. 2t is the derivative, x squared is the original function. Capital F of x, lowercase f of x, or f of t. Now, here's what we were talking about in the sense of it would be difficult. Again, we could do it on our calculators, but it would be difficult to geometrically find out what the area under this curve is by hand because these are not nice, pretty lines or circles. And so these are not common shapes that we're able to take the derivative of. To find the area of. And so here is where the fundamental theorem of calculus comes into play. And this is what I need you guys to write into your notes. It says, if a function f is continuous on a closed interval from a to b, and f is an antiderivative, so just like we were doing in the very, very first lesson where we were looking at antiderivatives, it says that if you take the integral from a to b of f of x dx, it's the same thing as looking at the original function and evaluating at b, and then the original function evaluated at a, and subtracting them. And that will give you the exact area under the curve. No approximations, no needed Riemann sums. We don't need to calculate any geometric areas. If we are able to algebraically figure out the integral of lowercase f of x and come up with an expression for it in terms of capital F, then we can just evaluate at the two limits of integration and subtract to find the exact area under the curve. And that's called the fundamental theorem of calculus. So here's some examples. It says find the values of the definite integrals below. The first one. Again, the first thing that we'll do is we will go ahead and find the integral of x squared. So if you think back to the very, very first lesson we talked about in this semester, we said the integral of x squared is x to the third power, bump up the exponent by 1, and divide by the new exponent. So that's x cubed over 3. And then we had a plus c. Now here's a notation you guys are going to have to start becoming familiar with. We're going to draw a vertical line. We're going to draw from 1 to 2. Now, technically this plus c won't be here anymore, and I'll explain why that is in just a minute. But that vertical line with the limits of integration, that kind of is a way for you to notate that you're keeping track of what your limits of integration are, that they haven't gone away. And we don't want to keep writing them in integral form, like some people get tempted to rewrite the integral but then leave the integral symbol there and put from 1 to 2. We don't want to do that because that's not correct notation. So this is the correct way to actually write this. Now, the fundamental theorem of calculus says, once we've come up with an expression that represents the antiderivative or that represents the integral, we're going to plug in both of these limits of integration. We're going to evaluate this function at 2 and evaluate this function at 1, and then subtract them, f of b minus f of a. If I plug in 2, I get 2 cubed over 3 plus c, minus, if I plug in 1, I get 1 cubed over 3 plus c. So 2 cubed is 8 thirds plus c minus 1 third minus c if I distribute that negative. So here's why we're no longer going to write the c's. Every single time that will happen where you get c minus c. And that's because the constant of integration will always be the same in both of these regards. And so they're always going to get rid of each other. So when we're evaluating a definite integral, we do not need to write this plus c, only if we're working with indefinite integrals. So we have 8 thirds minus 1 third, and 8 thirds minus 1 third is 7 thirds. So that is the exact area underneath the curve of x squared in between 1 and 2. That's called a definite integral. Let's look at example 2. The integral of 3x squared is 3x cubed over 3 minus 2x squared over 2 minus 1x. And again, I'm not going to write the plus c because I know that as soon as I do the fundamental theorem of calculus, it's going to go away. So we'll just say this is the integral of, we're going to evaluate using the fundamental theorem of calculus what this function is the exact area under the curve from negative 1 to 3. So if I simplify this a little bit first, I get x cubed minus x squared minus x from negative 1 to 3. If I evaluate at 3 first, I get 3 cubed is 27, minus 3 squared, which is minus 9, and then minus 3. And don't forget the fundamental theorem of calculus has a big old subtraction in the middle. It's f of b minus f of a. If I plug in negative 1 cubed is negative 1, negative 1 squared is positive 1, so that's minus a positive 1. And then a negative x, if I plug in negative 1, I get negative 1 to be plus 1. So 27 minus 9 is 18. 18 minus 3 is 15. Minus negative 1, that's negative 2, plus 1 is back to minus 1 again. So 15 plus 1 is 16. And that's the exact area under the curve of 3x squared minus 2x minus 1 in between negative 1 and 3. By the way, the order does matter. It matters that you plug in f of b first and then f of a and subtract them in that order. If you do it the other way, you're just going to get a negative answer. For example 3, we have x to the 1/2. So this is the integral from 0 to 9 of x to the 1/2 dx. So again, taking the integral, if I bump up my exponent by 1, that would be x to the 3/2 over 3/2. I'm not going to write my c because I know this is a definite integral. I'm just going to evaluate from 0 to 9. So this is 2/3 times 9 to the 3/2 minus 2/3 times 0 to the 3/2. Now 9 to the 3 halves, remember that this is 2/3 times the square root of 9 cubed. And then 0 to the 3 halves is just 0, so minus 2/3. The square root of 9 is 3. 3 cubed is 27. So this is 27 times 2/3 minus 2/3. 27 times 2 is equal to 54. So this is 54/3 minus 2/3. And then 54 minus 2 is equal to 52. So the final answer is 52/3. And that's my bad. I just found an error, actually, so help me fix this on your paper. 0 to the 3 halves is 0, but I forgot to multiply it times 2/3, so I accidentally multiplied it and left it. 0 times 2/3 should be 0, so we should erase this piece of it where we said minus 2/3. And so our final answer is actually 27 times 2/3, which is, if I simplify 27 and 3, are both divisible by 3, so this would be 9 times 2 over 1, which is 18. So final answer should be 18, not subtracting the 2/3 at the end. My bad. All right, let's keep going. On these ones, we have a little bit of rewriting to do before we're able to actually take the integral. For this first one, the 2/3 that we have right here, this 2 and this 3, these are constant multiples, so I'm going to pull them out front since they're just going to tag along for the ride. So I'm going to rewrite this as 2/3 times the integral of 1 over x squared dx. And I'm going to rewrite that as 2/3 times the integral of x to the negative 2 dx. And my limits of integration are from 5 to 10. If I actually evaluate the integral now, I get 2/3 times x to the negative 1 over negative 1, evaluated from 5 to 10. If I simplify that a little bit before I evaluate, it's a negative 2, and then that x goes to the bottom, so that's 3x on the bottom, evaluated from 5 to 10. And now if I do the fundamental theorem of calculus, I plug in 10 first, that's negative 2 over 3 times 10. Minus f of a, so negative 2 over 3 times 5. That gives me negative 2 over 30 plus 2 over 15. If I simplify, that's negative 1 over 15 plus 2 over 15 is equal to positive 1 over 15. For this next one, in order to take the integral of this, I want to multiply it out first. So this is negative 1 to 1. If I multiply out 2x minus 1 squared, that's the same thing as 2x minus 1 times 2x minus 1, which is 4x squared minus 2x, so minus 4x plus 1. The integral of this then becomes 4x cubed over 3 minus 4x squared over 2 plus 1x, evaluated from negative 1 to 1. If I plug in 1 first, I get 4/3. This simplifies to 2, so minus 2x squared would be minus 2, and then x squared would just be 1 still, so minus 2, plus 1, minus fundamental theorem of calculus is to subtract. And now let's plug in negative 1. So this would be a negative 4/3. If I plug in negative 1 here, negative 1 squared is still 1, so this is still minus 2. And then if I plug in negative 1 here, that becomes a negative 1. So we have 4/3. Here we have minus 2 and minus 1. I'm sorry, minus 2 and plus 1. So that's minus 1. Minus negative 4/3 And in here we have -2 and -1, so that's -3. If I distribute the negative, I get 4/3 minus 1 plus 4/3 plus 3. If I do a little combining of like terms, that gives me 8/3 plus 2. That's 8/3 plus 6/3 if I want to combine these fractions, which ends up giving me 14/3. Final answer. All right, with number 6, I want to rewrite this one again. So I have the integral from 1 to 8. And then I'm going to break this apart into two separate fractions. X over x to the 1/3 minus 2 over x to the 1/3 dx. If I rewrite this again, I have the integral from 1 to 8 of, if I subtract these exponents, that will be x to the first over x to the 1/3. 1 minus 1/3 is 2/3, so that's x to the 2/3 minus 2, and then I'm just going to bring that x to the -1/3 up to the top. So now let's actually go through and take the integral. The integral of x to the 2/3 is x to the 5/3, bump up the exponent by 1, divided by 5/3, minus 2x to the -1/3 plus 1 would be 2/3, divided by 2/3. And this is from 1 to 8. All right, I'm going to erase some of this over here so we can have enough room to write this all out. All right, so if I rewrite this, this is 3/5 x to the 5/3 minus 6/2, which is 3 x to the 2/3 from 1 to 8. If I plug in 8 first, that would be 3/5 times 8 to the 5/3 minus 3 times 8 to the 2/3 minus 3/5. If I plug in 1 to this, that would just be 1 to the 5/3, which is 1. So I'm just going to leave that as 3/5. If I plug in 1 to this, that would be 1 to the 2/3, which is just 1. So I'm going to leave this as minus 3. So we have 3/5. If I want to rewrite this, it's the cubed root of 8 to the 5th power minus 3 times the cubed root of 8 to the 2nd power minus 3/5 minus 3. All right, let's try to do a little bit of this in our head. The cubed root of 8 is 2. 2 to the 5th power is 32. So this is 3/5 times 32 minus 3 times cubed root of 8 is 2. 2 squared is 4. Minus 3/5, I'm going to distribute this negative now, and then plus 3. So I just distributed that negative to both of those, so I could change their signs. All right, that's a lot of work for this problem. 32 times 3 is 96 fifths. 3 times 4, minus 12, minus 3/5 plus 3. 96 fifths minus 3/5 is 93 fifths. Negative 12 plus 3 is negative. If I get a common denominator, that's 93 fifths minus 45 fifths. Excuse me. And 93 minus 45 is equal to 48 fifths. And that is the final answer to this problem. I know it's a long, drawn-out problem, but that's how you get the final answer to this one. All right, these are our last 3 problems for today. On this first one, it's a little easier to take the integral of, actually. The integral of 2 is 2x. The integral of sine, if you have your little cheat sheet out, the integral of sine is negative cosine. So let me change that to be a negative cosine of x. And again, I'm not going to put plus c because we're working with definite integrals, not indefinite. And the integral is from 0 to pi. So if I plug in pi, I get 2 pi minus cosine of pi. Fundamental theorem of calculus says to do f of b minus f of a. If I plug in 0, I get 0 minus cosine of 0. So this is 2 pi minus cosine of pi is equal to negative 1 minus 0, and then plus cosine of 0 is equal to 1. So this is 2 pi plus 1, which is 2 pi plus 2. For this next one, the integral of 4x is 4x squared over 2. The integral of secant squared is tangent. And this is from 0 to pi over 4. If I plug in pi over 4 first, well, first of all, 4 divided by 2 is 2, so this is 2x squared. If I plug in pi over 4 first, I get 2 times pi over 4 squared plus tangent of pi over 4. Minus, if I plug in 0, if I plug in 0 here, that's just going to be 0. If I plug in 0 here, I have tangent of 0. So this is 2 times pi squared over 16, which simplifies to, the 2 and the 16 both have a divisor of 2 they can take out, or a factor of 2, I should say. So this simplifies to 2 pi squared over 16, which will be pi squared over 8. Tangent of pi over 4, if you use your left-hand rule, tangent of pi over 4 is equal to 1. And then tangent of 0. Tangent is sine over cosine. Sine of 0 is 0. Cosine of 0 is 1. So this is 0 divided by 1, which is 0. So tangent of 0 goes to 0. Or equals 0, I should say. So my final answer, pi squared over 8 plus 1. And last but not least, number 9. On number 9, we've talked about this before, that you could technically write a piecewise function from this. But it's probably easier if you just graph it. So I'm going to plug in some numbers in between 0 and 5 to figure out what it looks like. And then once we have some numbers and a graph, then it should be easier to actually calculate the area geometrically. So I'm going to erase some of this other work just so we have some room. So if I graph this, I'm going to make a little XY chart. And I'm going to plug in some values in between 0 and 5. So I'm going to plug in 0, 1, 2, 3, 4, and 5. If I plug in 0 here, let me write it over here so it's easier to see. If I plug in 0, I get 4 minus 0, which is just 4. If I plug in 1, I get 4 minus 2, which is 2. If I plug in 2, I get 4 minus 4, which is 0. If I plug in 3, I get 4 minus 3, which is, 4 minus 2 times 3, which is 4 minus 6. That's negative 2. But because it's absolute value, it's a positive 2. If I plug in 4, that's 4 minus 8, which is negative 4. Absolute value turns it into a positive 4. If I plug in 5, that's 4 minus 10, which is negative 6. Absolute value turns it into a positive 6. If I plot these points, 0, 4, 1, 2, 3, 4, 1, 2, 2, 0, 3, 2, 4, 4, and 5, 6. It looks like this. So by doing that, now I'm able to calculate the area under the curve using geometric shapes. So I have a triangle right here. It has a base of 2 and a height of 4. 4 times 2 is 8. Half of that is 4. So the area of this is 4. And then I have another triangle over here. The base is 1, 2, 3. The height is 6. 3 times 6 is 18. Half of 18 is 9. So this has an area of 9. Therefore, back up here with this integral, the integral from 0 to 5 would be 4 plus 9, which is 13. So there are algebraic ways of evaluating the integral of an absolute value, but like I said, the easiest way is probably just to graph it. And then the last thing you need to know is that we are able to calculate integrals on our calculators. It's difficult for me to show you how to do it, so this video does it for you. So this is how to do it the old way. If you read this, if you have one of the old calculators, this is how you would do it. But with your new calculators, click on this picture right here, and it'll take you to a YouTube video. And the guy in the YouTube video shows you how to use your calculator to calculate the definite integral. And that way you can use it on tests and quizzes and things like that when you're able to. So make sure to watch that video. Don't finish today's lesson until you watch that video. And you're not able to click on it. Well, you are in the PowerPoint. Obviously, we are in a video right now. You can't click on my video to watch it. But if you go back to the PowerPoint, the link to the PowerPoint on the calendar, go to this slide on that link and then click on this picture, and it will take you to YouTube to go watch the video. So watch it, put it into your notes, write down the buttons you need to push in order to go and calculate the definite integral on your calculator, and you can go back and actually verify your homework problems and stuff to make sure you're doing them correctly. All right, go back and do that now. Don't think this is the end of your homework. Go watch. It's like a 4 or 5 minute video, and he does a couple examples just to show you guys. So go watch it right now.